Okay, so we just got done calculating the delta G under non-standard conditions using this equation, where we are calculating the position, the what they call reaction quotient. This guy, if you guys can recall, this dude right here, okay? This thing called reaction quotient. In other words, it's where the reaction is before it reaches equilibrium, which direction it's going to run. Okay? Well, you can probably guess then that you can easily calculate where the reaction is going to be once it reaches equilibrium. And that makes this really easy because we already have the equation set up. Here's the deal. If we let the reaction run until it reaches equilibrium under non-standard conditions, well, there's no more spontaneity. So at equilibrium, even if it is non-standard conditions, this value for delta G, notice that it does not have the little degree symbol after it, has to be 0. Well, that makes things pretty easy because if we take this reaction where delta G is 0, now what we have is this. 0 equals delta G under standard conditions plus RT times the natural log of K. Well, because delta G under non-standard conditions is 0, now we have this is equal to delta G under standard conditions. And that means that we can easily solve for the equilibrium constant simply by doing this. And of course, our buddy R is going to be our constant. R equals 8.314 joules over moles Kelvin, and T is temperature. All right. So pretty easy. That means you can find the value of the equilibrium constant when you are not at standard conditions. So let's take some data. Okay. Now this reaction, I could have solved for the delta H and the delta S for you, but you guys are pretty good at this stuff. Just remember that these guys are all in joules. So there's a couple ways you can approach this. You can either get all of these guys into joules by multiplying by 1,000, or you can get all of these guys into kilojoules by dividing. Well, this is already in joules. So let's just multiply delta H by 1,000, okay? So we're going to do this using all these delta H's from the reaction. And what we know is that the delta H for this reaction is going to be 2 times negative 826,000 joules minus nothing. Those are both 0, so that makes it easy. That gives us negative 1,652,000 joules. Easy peasy. Delta S. Well, this one's a bit more complicated, but not that bad. We're going to have 2 times 90 joules minus the sum of the reactants. We have 4 times 27 joules plus 3 times 205 joules. And you've got your handy calculator. So we can say 180 minus the quantity of 4 times 27 plus 3 times 205. And we get negative 543 joules. All right, well, here's how we calculate delta G from these data. Delta G equals delta H minus T delta S. We got everything into joules like good little scouts, so that's 1,652,000 joules minus the quantity. We're at 25 degrees Celsius, so that's 298 kelvins times negative 543 joules. So here we go. We're going to take negative 1,652,000. We're going to subtract from that the quantity, 298 times negative 543. And we get negative 1,490,186 joules. This is our delta G under standard conditions. What we're trying to find out is, because we're running this, and you're probably going to say, well, Mr. O, we're already under non-standard conditions, we're at 298. That's not what we're saying. We know the reaction is already spontaneous because the delta G, regardless, is negative. What we're trying to find out is, what will the delta G under non-standard conditions be when the reaction reaches equilibrium and the new delta G is 0. That's what we're trying to find. We're trying to find the value of K. All right? So that's what we're trying to find. And so here is our equation. We know delta G under standard conditions, which we just found, divided by the value for R times T. And we're already under non-standard conditions because we're at 298 kelvins. So you just calculated the delta G, negative 1,490,186 joules. The value for R, 8.314 joules over moles Kelvin. And let's put that moles in there just because. And our temperature is 298 kelvins. And that means all of our units are going to cancel out, which is what we want. Okay, so here is our natural log of K. We got negative 1,490,186 divided by the quantity, negative 8.314 times 298. I get 601. So to find K, we're going to take the E of 601, right? And we get a very, very, very large number. We get, oh my goodness. Excuse me, wrong one. We get 1.02 times 10 to the 261. That number is huge. Holy mackerel. Means the reaction is very spontaneous because it favors the products in an immeasurable ratio, that big. Okay? So that's all I'm asking you guys to try. What is going to be our equilibrium position when the non-standard conditions bring our delta G to 0. In other words, what is the value of the equilibrium constant when the reaction stops being spontaneous? Okay, give it a try.